All right, so we're on to 3.5, part 2, day 2 here, looking at modeling with exponential and logarithmic models. So we're going to look at 3 different types today: Gaussian, logistic, and logarithmic. So we're going to look at 3 different types of formulas or equations that people use to model. So yesterday we just did sort of basic exponential growth and decay, and if the rate is positive or negative determines if it's growth or decay. The other 3 are called Gaussian, logistic, and logarithmic. So let's talk about those 3. And then again, not a completely exhaustive list, but these are just to give you some other ideas of what this can look like. So Gaussian looks like this: y equals a, and then e to, then just be real careful up here, negative x minus b quantity squared, and then divided by c. So that whole thing's up in the exponent. So the a, the b, and the c are specific to that particular model. So kind of a crazy looking one. Logistic looks like this: y equals a plus b times the natural log of x. So using a log, natural log, so they call that logistic. Logarithmic models, oops, I'm terribly sorry. I put that in the wrong spot. Logistic is this one: a over, that was doing the next one, 1 plus b e to the negative x. Sorry about that. Make sure you make that adjustment. A over 1 plus b e to the negative rx. I'm just falling apart here. B to the negative r. So you need my interest rate in there. So the a, the b, and the r are the things that would be unique to a logistic. Logarithmic growth or decay are looking like this, the one I wrote by accident before. So a plus b times the natural log of x, or you can do a plus b times the common log of x. So just depending on what model fits better. So Gaussian, logistic, and logarithmic. So they all are using different types of equations to be able to solve. Oh my goodness, and I forgot to write the e to the. Oh my goodness. So be careful. Take a look back. I apologize. For logistic, I'm just having trouble writing that one for some reason. A over 1 plus b e to the negative rx. Okay, so let's take a look at some applications on what these things look like. So I'm going to show you just an example of what each of those models actually look like when you graph it, kind of like the parent graph versions, like the easiest. So e to the x, e to the negative x, we know what those look like. Gaussian, make that sort of Gaussian type curve, or that bell-shaped curve. So things that are raised e to the negative x squared, that's the kind of thing that you're going to see for those. Our next ones, let's take a peek. Logistics, something like that. You have this awesome asymptote thing happening, horizontal asymptotes with different kinds of growth in between. So it grows very quickly initially, followed by kind of a flattening out towards another asymptote. So we'll talk a lot about that different kind of behavior, but lots of real life things do that actually. Natural log models, so just graphing natural log with different shifts. So we know all about that, and it can be either common log or ln. And there are a lot of real life things that follow log growth models as well. So we're going to take a look at examples of all of these things, and we'll be graphing on our calculator too. So let's start with Gaussian. So we'll dive into those. So Gaussian models are used a lot in probability and stats to represent populations that are normally distributed. So when we think about the normal distribution or normal curve that you guys talk about in Algebra 2, so a Gaussian model, what that means is the average value for a population can be found from this bell-shaped curve by finding the maximum y value. So that maximum y value corresponds then to the x value that is the average for that population. So I'm going to go ahead and draw this so you can see what I mean, and then we'll kind of label that and you can write that in. So if you take a look at any Gaussian model, you're going to have something like this where you have this bell-shaped curve. The maximum y value up here, so whatever the most in that population is, corresponds to the maximum or the average value of the x's. So this is the average value of whatever x is. So like if it's the average test score or the average age of your population, whatever it means. So the average is what we have at that maximum location. So wherever your maximum y is, that corresponds to the average of the population set for x. So if you can look at the distribution and find the maximum point, then you know where that's going to happen. So if you think about it in really big population sets or data sets, the average is going to happen at the most number of values. So that kind of makes sense. If you think about the average number in the data set is going to occur and have the most values with it, and as you go out to either end, it's going to tail off. There's less people that are going to be really high, there's less people that are going to be really low. The most is going to occur at the average, so at that maximum. So let's take a look at a great example of that. We're going to take a look at an SAT example. This would be the same for ACT. So this is for the 2015 results. So this is the actual model. In 2015, that math score, so we're just going to look at the math part, for college-bound seniors in the U.S. was roughly followed this distribution. So here is the equation. So you can see why they consider that Gaussian. So if we go back to our model, that third one here, A e to the negative x minus b squared over c. So the a, the b, and the c are particular to that data set. So when we look at that, we have that e to the negative has that format. Between 200 and 800 are what your x values are. Now, if you know something about the SAT, what kind of scores you can get, 800 is the maximum score that you can earn on the math portion of the test. 0 would be nothing, obviously. So when you look at that 800, that's what they're talking about. So the X is the SAT score for math. So they're talking about the scores there. We're going to take a look and we're going to try to graph this and see if we can figure out the average SAT score for math. Now remember where the average is going to occur. If we can find this maximum value of the distribution, the X value that goes with that maximum point, so whatever that X is, that's the average, because the average is going to occur at the most number of data points, or the most people that scored average, right? Most people score average on that SAT. There's way fewer kids that get perfect scores of 800, way fewer that get almost nothing. The most number of kids are going to score at the average. So we're looking for that point. So if we can graph it, we should be able to figure it out, because solving this equation would be pretty nasty. So we want to see if we can figure out what that is. So let's see if we can go ahead and type that into your graphing calculator. Be really careful, and then we're going to compare. All right, so I typed this in so you can see how I typed mine. Just be careful, and then we're going to have to set up the window so we can see this. So they want us to go from 200 to 800 for our x, so let's go ahead and get that in there. So 200 to 800. I don't know, I'll go by hundreds, it doesn't really matter. And then do we need any below? Well, this is number of students. So I think we can start at 0 here and then go up to like the maximum number of students who have taken it. Let's see. I think I tried something that worked, so let's just go with the flow here on this for me. I think I have it at 0.004. Let's see if that checks out for a graph here. There we go. So I kind of played around with this to get something that works well. Okay, so taking a look at the curve, how would you figure out the average score for the ACT or the SAT then? Remember, the average occurs, the X value of the maximum on the graph. So we're going to try to find that maximum, which we know how to do. So we're going to do a second calculate. We want a maximum. We're going to go left bound a little bit to the left of it, and then right bound a little bit to the right of it, and we're going to make our guess. And it looks like it's at 511. Okay, so 511. So I'm going to go ahead and kind of move this out of the way so you can see kind of that exact thing. And this was happening at a score of 511. So that means the average SAT math score was 511. Now, if you think about 800 being the maximum, 511, decent score. That's where, so half of the population scored above a 511, and then half of the population scored less than that. So that maximum happens at the average. So the most number of people scored the average score. Now, take a quick peek back at the equation. Do you see 511 happening anywhere there? Look at what's inside here. Remember, that's your shift, right? So a horizontal shift with the X going to the right, 511's right there. So what if the average score was 520? Then you'd see a 520 in there. So you can actually look at these Gaussian representations and you can tell the average if you know where to look in that equation. Any guesses on what that number represents? That was the total number of kids that took the test. So dividing by that average. So when we think about like standard deviation, where that's coming from, we're finding the difference in the X's and then dividing by how many scores or how far you are from the mean. So standard deviation away from that average, that's where that number is coming from. All right, let's take a look at another kind of model. So let's look at logistic. So logistic growth models, are a rapid growth, and then followed by a declining rate of growth. And they are bounded by two horizontal asymptotes. So we have a horizontal asymptote, another horizontal asymptote. I'm going to draw the picture first, and we'll talk about what would do this. So initially, we have rapid growth, and then followed by declining growth. So the initial part, things are growing very quickly. So we start off with a region of rapid growth happening here. And then it's followed by a period of slower growth. All right, so can you think of any real life things that do that? Initially grow really, really fast and then kind of slow down and even out and approach an asymptote. Think about, how about the growth of a baby? So it starts out initially, grows, so it gains weight and height and all of that really, really quickly. But then eventually you kind of level out, you slow down, you don't grow as quickly, and then you reach, like, say, your maximum height. So you get to that particular point. You don't just keep growing infinitely forever. That would be creepy. So like that's a really good example to see what that could look like. Or you could look at sales of something. So sales of a say an iPhone. So initially, it's a new phone. It's really cool. We sell a whole bunch of them. But then the growth kind of tapers off as the technology gets older, newer ones come out, and then it eventually kind of plateaus and you approach this other asymptote where you are um, reaching a point where they're not going to sell anymore. So if you think about it, that actually happens actually quite a bit in real life. So think about what these asymptotes represent. This would be like the maximum value you could ever be. So like your maximum height, and this would be the minimum value it ever could be. So when you're starting at the bottom. So those asymptotes kind of represent the boundaries of what values you're looking at. So let's take a look at a great example. And this one kind of apropos uh, for life. We're looking at the spread of a virus, which, as I'm recording this, is really a big deal in 2020 here. So when we think about how this it grows initially very, very quickly, right, spreads, and then hopefully tails off, and we reach a maximum value when, in this case, a maximum value would represent when everybody had the virus, right, that you couldn't have any more people than what you have the virus. The minimum value would be no people having it. So think about those asymptotes, what that means. So on this college campus, there's 5,000 students. One returns from vacation with a contagious, long-lasting flu, and this is what it's going to be modeled by. Notice where the 5,000 is that maximum value that we have. So this model, this logistic model will govern how many students have the virus after T days. So Y is the total number of students infected after T days. The college is going to cancel classes when 40% or more of the students are infected. We're dealing with a lot of this public health initiatives and trying to figure out what's safe and all of that. So this was kind of pre all of those conversations. So let's take a look. How many students are infected after 5 days? So I can just put in 5 for T and solve. So we're going to go ahead and just type that in. All right, so just be really careful. Make sure you get that parenthesis in the bottom. So 5,000 divided by that, we're putting in 5 days. Looks like 54 kids. Now let's talk about the rounding. Can you have 0.01 of a student? No. So we want to round to a whole number to make sure that we're thinking about something that's going to be appropriate. So 54 students after 5 days would be infected. Now, let's talk about the canceling classes part about this. So it's growing pretty rapidly. After how many days will the college cancel classes? Well, that'll be when 40% more of the student body are infected. So if you have a campus of 5,000 students, we need to figure out what that threshold is. So we need to figure out what 40% of those 5,000 students might be. All right, so what's 40% of 5,000? Would be about 2,000 students. So 5 days is, we're definitely still fine because there's only 54 kids that are sick. We want to figure out when we get to 2,000 students. So when is that going to happen? Now this might look like a pretty ugly equation to solve, but we can actually solve for t. This is an exponential equation because the t isn't an exponent. The work to do to solve this just takes a little bit, but we need to get that out of a denominator so we can actually deal with it. So remember, when we don't want something in the denominator, we're going to multiply both sides of the equation by that denominator. So I'm going to multiply both sides by the 1 plus 4,999e to the negative 0.8t. So over here, we're going to have 2,000 times that denominator And then all I'll have left on the other side is the 5,000. Okay, now remember our whole idea about isolate the exponential. I'm going to try to get this by itself. I think for me, I'm going to go ahead and instead of distributing the 2,000 through, I think I'm going to go ahead and just divide by it because I think the numbers are going to be a little bit easier to deal with. And then I can just have a 2.5, which is not super, super difficult to deal with over there. And then now we're going to subtract 1. So 4,999 e to the negative 0.8t equals 1.5. Okay, then I need to deal with multiplying by 49.99. So divide by that. So it's a lot of algebra, but it's pretty basic things that we've been doing, nothing too crazy. So I'm just going to go ahead and leave it 1.5 divided by 49.99. I know that's not a nice number. Okay, so this is exponential, right? So we're going to use inverse operations. We're going to rewrite it as a log. So that would be natural log. So log base e of, here's my argument, 1.5 over 49.99. And that's going to be equal to our exponent, negative 0.8 times t. So all that's left to deal with, we're going to divide by that negative 0.8. So it seemed like kind of a ridiculously horrible looking thing, and there was some work to do to solve it, but we can solve for, hey, how long is that going to take to get to 40% of the kids infected? All right, so typing that in, again, make sure you finish off that parenthesis, 10.139, so a little bit over 10 days. Now that's really fast growth because we went from like only about 54 kids infected after 5 days. After 10 days, we're already up at 2,000. So that's really initial rapid growth here. So we're at about 10.14 days. So 10 days into this, the college would be shutting down and canceling classes. So again, think about what those asymptotes are really representing then. The most number of students that can ever get this is going to be the 5,000. We're starting with no cases down here. So this initial rapid growth, and then it slows down until eventually no one else can get it because everybody had it. That would be like kind of the worst case scenario. We'd hope that we could kind of catch it before then and we wouldn't have any other issues. All right, let's take a look at a couple last logarithmic models then. So we're going to go into this last model, just trying to show you some different things that can happen. Now this is kind of a crazy made up one. All the other ones have been kind of real data, but this is a sales model. So it says the number of kitchen widgets. So they're saying a widget is some, I don't know, kitchen tool that you're going to use in Y. So it's our Y in millions. So the number that are sold or demand is given by that equation, where x equals 0 represents the year 2000. So this is modeling sales growth. So a lot of log models are nice for growth because they don't grow quite as quickly as exponential does. So if you think about the pictures that I showed for the models, we're talking about these last two now. Natural log and common log, they're growing, right? But they're not growing as quickly as exponential. So it's usually a little bit more realistic to fit real life models to logs instead of exponential because the growth rate doesn't have to be as quick. So that's pretty common actually. It says find the year in which the number of kitchen widgets demanded was 8.6 million. In other words, that final amount was 8.6. So this would be a really straightforward kind of equation for us to solve. It's just a log equation. Ask yourself your questions. Do you see log on both sides? Nope. So it's not 1 to 1. So that means we need to isolate and we need to use the inverse. So we're going to be doing those same things we always have. So go ahead, pause the video, see if you can isolate this and solve for x. So first thing I would do is subtract 2. So 6.6 equals 3 times the natural log of x plus 1. Okay, then need to get rid of that 3 out front. So that would be 2.2 equals the natural log of x plus 1. Or if it's easier, you can write natural log of x plus 1 is equal to 2.2 if you like your log on the left. All right, so now we've isolated. So now we're going to use inverse. Remember, this is base e. So we're going to rewrite it as an exponential. So e to the 2.2 is equal to our argument, x plus 1. And then we're going to subtract 1. So this is going to be e to the 2.2 power and then minus 1. So let's go ahead and type that in and see what we get. All right, so I typed that in, 8.025. So 8.025. What does that mean? What was this question even asking? It says, in what year? Remember, year 0 was 2000. So if I'm getting an x value of about 8, What year would that be? Well, that would be 2008. So in 2008, they would have reached that kind of demand. Why does a company need to know what demand it's going to have, or projections, accurate ones? So they know how much to produce so they can make a profit. This is really big business. So if you're a good mathematical modeler, it's really a great job, because you're going to be able to accurately predict things, and that's how companies can make money. All right, let's take a look at another example of a logarithmic model. So one of the most common ones you've probably heard of is a magnitude of an earthquake, or the Richter scale. That's a log model, so it's using logs to help calculate that. So the Richter scale, they use R for Richter. Richter was the person that this credited after. So this is talking about how intense an earthquake is. So instead of having to talk about the magnitude or the intensity value, they talk about it in terms of a log scale, because then you can look at just the power. Remember, logs are exponents, so we can look at just the powers instead of these massively large numbers. So instead of saying it's whatever 10 to the 7th power is, which is a huge number, right? We can say that it's just a 7 on the Richter scale. So that's kind of how the Richter scale is going to work. We use the power instead of that whole big number. So we can use this formula to be able to solve that. The I0 is sort of the baseline, like the initial intensity, which is a 1. So when they talk about that minimum intensity, that wavelength, that's always going to be a 1 value. So I naught, they would call that that basic value that we start with. So really, a lot of people will just say the log of I is equal to R, where I is the intensity, oh, it already says it up there, of the earthquake, and the R is the Richter scale value. So it's definitely just a log scale. So here's what I'm going to have you do. I'm going to have you compare the intensity for 2 earthquakes that happened in recent years, that were some of the most kind of devastating ones in recent history here. There's been more, obviously, but in central Italy, they had one that was a Richter scale measurement of 6.2, and in Mexico in 2017, they had a 7.1. Both very devastating. My question is, how much more intense was the earthquake in Mexico? Now, a lot of people look at 6.2 and 7.1, and they think it's not that big of a deal difference. It's only 0.9 difference, so it can't be that big of a deal. But actually, how much is that in terms of magnitude, intensity? So if you take a Richter scale measurement of 6.2, and figure out the intensity, versus a Richter scale measurement of 7.1 and figure out the intensity. Is it really just 0.9? Is that all it is, or is it a lot more intense than that? Because 0.9 bigger doesn't seem like all that much. It's less than 1. Okay, let's solve for it. So this is a log statement, right? Log of the intensity is equal to 6.2. Remember, that's a base 10. That's a log sentence. There's not log on both sides. It's not 1 to 1. We're just going to rewrite it as its inverse. So 10 to the 6.2 would be equal to the intensity. For this one, it would be 10 to the 7.1 is the intensity. So the actual Richter scale measurement is actually the power. So if you think about what that means, then we're looking at a difference between 10 to the 7.1 and 10 to the 6.2. So how much more intense would it really be? Well, 10 to the 6.2, go ahead and type that into your calculator. And 10 to the 7.1, go ahead and type that into your calculator. And let's make that comparison. So I'm just going to round to whole numbers just to make life a little bit easier here. So how many times stronger was the one in Mexico? Well, it would be 10 to the 7.1 over 10 to the 6.2. Like, how many times bigger was it? Or this 12 million number divided by the 1 million number, which is about 7.9, or almost 8 times more intense. So when you look at, more intense is what I was going to write. When you look at these Richter scale numbers, and I think it's easy to be, it's only about 1 bigger. Well, that's actually 8 times more powerful when you look at the values that they were. So you're looking at the exponents. So log scales are a way to describe very large numbers in a way that's easier to report. It's much easier to report 7.1 than this number 12,589,254. So log scales can be really helpful in describing modeling real life situations. All right, so we talked about these last models then today. We talked about Gaussian, and we talked about logistic and natural and common logs, being able to work with them and model real life situations.